So we're starting today, just kind of let's rewind a little bit and go back to where we were at the end of Friday's class. So on Friday, we went through and looked at this kind of way of looking at matter from a standpoint of composition. So if you go back to this flow chart that we made, we were able to classify matter into one of four categories based upon some simple ideas. Does it have a uniform composition? Does every single particle in that substance look the same? If it was, then we called it a pure substance. If it did not have that kind of uniformity in composition, we called it a mixture. And then from there, we looked at, well, what makes pure substances stand out from each other? Well, how about what they're composed of? Are they made up of one kind of material, one kind of atom, and are elements? Or are they made up of multiple atoms and are compounds? And on the mixture side, do they have uniformity of appearance, where I can't tell one component from the other? And we call those solutions or homogeneous. Or is there something about them that I can tell very quickly apart from a physical standpoint? And so from that standpoint, we were able to kind of put matter into groups based upon those kind of ideas and subgroups. What we're going to start with this afternoon is we're going to look at, well, how do we describe matter in different kinds of ways? And what we'll find is that when we describe matter and try to put some different kinds of descriptors on it, they're going to break down into two main categories: the physical properties and the chemical properties. Now, the difference between those two has a lot to do with what's happening to the substance as we observe them. If we are describing a physical property, that is a property that we can describe without changing the composition of the substance itself. Whereas chemical properties, in order to observe them, we must also change their chemical composition, or at least attempt to change their chemical composition. So let's take, for example, this block of salt. What are some things that I can observe about this particular sample of rock salt? Well, I can observe that it is a solid. I can observe that color-wise, it is, well, it's kind of has no color. Maybe we could call it white, maybe we could call it colorless. It forms crystals that are blocky and kind of rectangular in shape. It is something that if I had a ruler, I could probably measure its dimensions. If I had a balance, I can measure its mass. So those would all be examples of physical properties, things that I can observe or even measure that wouldn't change the chemical substance itself. Chemical properties, on the other hand, would be, well, what if I took that salt crystal and I tried to burn it? Well, what I would find is that the salt crystal would not burn. That would give me an idea about the chemical property of flammability. We would describe salt as non-flammable or not flammable, as opposed to something like gasoline, which is highly flammable. Could I try to observe the acidity or the basicity of this salt crystal? Yeah. And again, that would be a chemical property because in order to observe acidity or basicity, I'm going to have to do some kind of a chemical reaction with it. Either expose it to litmus paper and try to change the chemistry of the litmus, or some other kind of chemical kind of example. So when it comes to chemical and physical properties, again, the things that we can look at are on the physical side, we're looking at mostly observables, things that we can monitor with our senses that would not change the actual identity of the substance itself. So things like odor, melting point or boiling point, measuring just the temperature of it itself would be a physical property. I can measure the temperature of this room without changing anything chemically inside of it. And you can see on the screen there are other kinds of physical properties, some of which I mentioned, some that I didn't. Certainly we can observe the taste of the salt if we wanted to. You could put a rock crystal and lick it and see what it tastes like. But notice that in physical properties, we have a combination of qualitative, that is things that we can observe without numbers, and quantitative, things that we can observe with numbers. So for density, that's one we would have to measure with numbers. We're going to have to measure the mass of the salts. We're going to have to measure the volume of the salt. We're going to have to do division to figure out what the density actually is. Well, whether it's measurable or not measurable, whether it's an observed property or a measured property, so long as we aren't changing the identity of the substance, we would call it a physical property. Now, contrast that with chemical properties. Chemical properties are ones where we would have to observe some kind of chemical transformation taking place while we are observing the property itself. So some examples of this: rusting or oxidation. That's a chemical property. When iron rusts or oxidizes, it undergoes not only changes in its physical appearance, but also changes in its chemical composition as well. Flammability. When something is burned, it has not only a change in physical appearance, but we also see a change in chemical identity as well. And so the other examples here are notable as well: acidity, basicity, toxicity, corrosion, capability, corrosiveness. They all can kind of play into that. What's important, though, is we have to understand something else about chemical properties. The lack of that property is just as important as the property itself. When we describe something as flammable or non-flammable, those are still both chemical properties. They're both important pieces of information about that substance that tells us a lot about storing and reactivity and other kinds of things. So just because a substance lacks that particular chemical property, that's still an important piece of information to know. When matter undergoes changes, we can put those kinds of changes into categories as well: the physical and the chemical change. Now, the thing that we have to understand and need to know is that physical and chemical changes have a lot of the same kinds of definition and descriptors associated with them as what we saw with physical and chemical properties. So the distinguishing factor between physical and chemical properties was whether or not the substance changed, right? It's the same thing here. The difference between a physical change and a chemical change has to do with the composition of the substance. In a physical change, we notice some kind of change in appearance, but yet the substance itself does not change at all. A great example of this is water boiling. So if I were boiling water on this coffee pot here, what I would notice is that over time, the water would start to bubble up as we heated it, and we would start to see the water vapor, this steam, coming off of the pot. So we are seeing an observable change. We're seeing the liquid water turn into water vapor or gaseous water. But what we are not seeing is a change in the composition of the molecules that are there. The molecules in the gas are still water molecules. They still have 2 hydrogens and 1 oxygen. The water molecules in the liquid are still water. They still have 2 hydrogens and 1 oxygen. So from a compositional standpoint, they are identical to each other. All that we've done is we have changed the appearance by adding energy to one of them. By adding energy to the water, we've increased the molecular motion of those water molecules to such a degree that they actually break forth from each other and separate out and take on the properties of a gas. So if you remember from our discussion on Friday, the differences between solids, liquids, and gases. Liquids, everything's all clumped together and clustered and touching each other. In gases, they're all far apart from each other. What is the difference? Why do we see that in general? Main difference is energy. The energy of the molecules in the gas phase is way higher than the energy of the molecules in the liquid phase. And if we heat it up, we can provide that energy enough to get that change to take place. So one thing that we need to know is that all changes of state are in fact physical changes. Now, in total, there are 6 changes of state. So solids, we know, can go from solid phase to liquid, solid phase to gas. Now, these processes, probably familiar at least with some of them, we know that if we go from the solid phase to the liquid phase, we call that melting. If we go from the solid phase to the gas phase, we call that sublimation. Liquids can go from liquid to solid or liquid to gas. We know from experience that when we take a liquid and turn it into a solid, we freeze it. So this process is known as freezing. And for liquid to gas, we generally call that boiling. Although there is a second term in here to describe non-boiling, evaporation is the conversion from liquid to gas at a non-boiling temperature. For gases, we can see gases turn into liquids or into solids. The first process is called condensation. The second process is called deposition. Of the 6 processes, we're probably less familiar with these two just because we don't have as many good examples of it. Condensation, we're probably a little bit more familiar with. This is more or less what is happening when fog forms. This is also what happens when you get water droplets on like your windows or stuff like that. See this maybe more in your bathroom. You take a hot shower, the water vapor from your shower ends up fogging up your mirror. Deposition, the most common process that we know for that is actually snow. In the upper atmosphere, you've got clouds. Clouds are big collections of water vapor. When that water vapor crystallizes around a dust particle, it forms a snow crystal or snowflake, and that snowflake eventually falls down. So that's probably the most common example that we have for deposition is just the fact that snow exists. But all of these are physical changes. In none of these processes do we see the identity of the substance actually change. All that is changing is how those molecules are interacting with each other. Are they clustered together or are they far apart? Are they able to move over each other or are they fixed in place? And the main difference between all of them is just energy. So what do all these ones that are highlighted in yellow have in common? They all require energy to run. It takes energy to melt something. It takes energy to boil something. It takes energy to sublime something. These other processes, which we will highlight in red, all of these processes actually release energy. So in the act of freezing something, you are causing the energy inside of those molecules to leave, which allows them to slow down and take on that more ordered or condensed kind of state. Now, on Wednesday, we'll actually throw out some terminology for there's a name for the processes that release energy. There's a name for the processes that require energy. We'll cover that in Wednesday's class. But we're gonna kind of build toward that as we go here. Let's talk now about chemical changes. Chemical changes are ones where we see changes in the composition of the matter itself. Like I said, one of the most common examples of this is combustion, burning stuff, flammability. And the reason why we can consider this so easily is because what we can see is that from a chemical standpoint, we started with butane. Butane's chemical formula is C4H10. And oxygen is O2. And so we start with this combination of oxygen and butane. And over the course of this time, we find that it turns into carbon dioxide, CO2, and water, H2O. So none of the substances that we started this particular reaction with are present at the end. Everything has been transformed into something else. Now, along the way, we get flames, we get heat, we get light. But we also get this transformation of the substances themselves. And so that's really the defining characteristic for how we tell a chemical change from a physical change. In both kinds of changes, we're going to notice something happening. We're going to notice that there's something going on. But really, the biggest thing that we're going to be able to tell is that the substances themselves are going to be completely different from what we started with. And that's how we know it's a chemical change. Now, there are some things that we can look for along the way. We can look for things like the evolution of heat, the evolution of light, the formation of a solid when there wasn't one before, the formation of a gas where there wasn't one before. Those kinds of things are also good physical things that we can look for. But composition is really the thing that we need to be focusing on. When chemical changes occur, we can monitor and track those chemical changes using a chemical reaction or a chemical equation. A chemical equation or reaction has basically three parts to it. You have on the left-hand side, the reactants. That is the stuff that you started with. On the right-hand side, you have the products. That is the stuff that you end the reaction with. And the products and the reactants are connected by an arrow to indicate that they have been transformed, that a chemical change has taken place here. So this is our first exposure to a chemical equation in its most simple form. And we need to understand that all chemical equations follow this kind of pattern. Reactants on the left, products on the right, arrow to connect and show the transformation between the reactants and the products. We always read reactions from left to right. So we'll summarize the first part of our discussion here today with this. The main difference between physical and chemical changes is the presence of a new substance. In a physical change, there is no new substance. We start with exactly what we ended, and vice versa. Everything that was there before is there in the exact same form after. With a chemical change, we do end up with the same stuff, at least in terms of all the atoms and stuff are the same, but they're now in different substances than they were before. We get new substances as a result of a chemical change. So let's move then into a couple of fundamental laws, things that we would talk about that would help us to describe chemistry more fully so that we can be more accurate in our description. And the first of these laws is the law of conservation of mass. Now, the law of conservation of mass and its very close cousin, the law of conservation of matter, basically say the same thing. Every particle, every atom that was present as a reactant is going to be present as a product. Matter cannot be created or destroyed in any process, whether that process is physical or chemical. And what this tells us is something relatively fundamental and simple. Everything came from something. So what we started with is what we ended with, and we're not going to lose anything along the way. So whatever atoms we start the reaction with, we're going to end with those same exact atoms. If it's a physical process, then all that we're going to see is that the particles are identical on both sides. If it's a chemical process, all the atoms will be there, but they'll be rearranged in some kind of way. Now, the reason we have framed this in terms of mass instead of matter is because when it comes to actually measuring this out, we have no way of accurately measuring the number of atoms of anything that are present, or the number of molecules of anything that are present. If I go back to that butane example, I have no way of accurately counting the number of carbon atoms that are in the sample of butane that I use. It's way too many to count. Nor do I have an accurate way of measuring out all the hydrogen atoms or all of the oxygen atoms that were used in the combustion process. I don't have a way of doing that. What I do have, however, is I do have a way to measure them in terms of their mass. There is a defined relationship between the mass of a sample and the number of particles in that sample. We just haven't gotten to that calculation yet in this class. But we know that it does exist. So rather than focusing on things from a matter perspective of atoms and molecules and particles, we can instead focus on a conservation of mass kind of perspective, where that is something that we can actually measure. I can measure the total mass of my reactants, measure the total mass of my products, and I should get the same thing at the end. That's what the law of conservation of mass tells us. Bringing this to a more concrete example. Let's look at that reaction between butane and oxygen. Now, if I were to measure out the amount of butane that I started with, let's say that, for example, I had 58 grams of butane. and I combined it with 208 grams of oxygen, I would get that the total mass of the reactants would be 266 grams. I'm just adding together the 58 and the 208. Now, if I were able to collect those products and measure the masses of those products, what I would get is that I'd have 176 grams of carbon dioxide and 90 grams of water. Put those together, I get the same 266 grams. The mass of the reactants, 266 grams, is equal to the mass of the products, 266 grams. Since the mass is conserved, we can make an assumption that matter is conserved as well, because matter and mass are directly related to each other. And so this would work for any kind of process that we wanted to go through. If we wanted to look at a chemical reaction, we could measure the mass of the reactants, measure the mass of the products, compare them to each other, we should get the same thing. If we wanted to look at a physical process, something even as simple as just taking a piece of paper and carrying it into a bunch of pieces. The mass of one tissue in its full and intact state should be the same as one tissue that has been ripped apart into pieces. Because in the end, if I find all of the pieces and put them together, from a mass perspective, it should be the same mass as the tissue was when it was intact. So it doesn't matter what the process is, if it's a physical one or a chemical one, matter should be conserved throughout the entire process. The last thing that we're going to talk about today is that of energy. Now, by definition, energy is the capacity to do work. Now, the question really is, well, what is work? Now, a physics book definition of work would be a force applied over a distance. And that works great for examples like, if I want to push this chair around, I can calculate the amount of work that I do by multiplying the force that I exert on the chair by the distance that I push the chair around. But the thing is, in the chemical sense, energy and work kind of are more restricted, more limited to things that we would talk about in a chemical perspective. So in your physics class, you might hear discussions about, okay, well, if I have this lever, how much force do I have to enact on it to get it to turn this much? Or how much energy do I need to put into a baseball to throw it from the pitcher's mound to home plate? Those kinds of things in, kind of practical terms. Chemistry deals more with things on the molecular scale, not exactly as easy to kind of put our heads around. So let's try to break these terms down into a more chemistry-focused kind of form. When we describe energy, we usually describe energy into one of two categories: kinetic energy, that is the energy of motion, or potential energy, stored energy. Now, in a chemical sense, kinetic energy can come in a variety of different forms, but we mostly will focus on things like thermal energy, that is the amount of energy that is being transferred as heat, whether it be coming from a chemical reaction or going into a chemical reaction, or things like electrical energy, the energy associated with moving electrons through a circuit, which can happen just by the sheer property of the substance itself. We talked on Friday about conductivity in metals. Or it could come from just the nature of a chemical reaction itself. There is a series of reactions that when we do them in the right conditions, they generate electricity for us. We call those redox reactions. You know them better as those are the reactions that take place inside of batteries. But that's all kinetic energy. There's something in motion here. Either we see an increase in molecular motion because of the increase of temperature or the decrease of temperature, or we see the movement of electrons in electrical energy. For potential energy, stored energy, most of the time when we're talking about that in chemistry, we're talking about that in terms of bonds. Chemical bonds, the things that are holding together a substance, have stored energy within them. Wherein if we rearrange those bonds, energy is either going to be required to break the bonds, or energy is going to be released in the formation of new bonds. So that's potential energy. Those bonds hold within them energy that can either be harnessed, or we need to input energy to actually break them. Nuclear energy, on the other hand, this is the energy that is housed within what holds together the nucleus. So inside the nucleus, we have protons and neutrons. What's holding together that nucleus? The answer to that question is something called nuclear binding energy. And if we snap that binding energy and release a whole bunch of energy from the nucleus as a result, we get radioactivity, but we also get the energy that's associated with nuclear power plants as well. So in chemical terms, kinetic energy, potential energy, we can think of these in terms of things like chemical bonds or heat that's being transferred in or out of molecules as the reaction proceeds. And so we come to this idea of, well, we talked about matter being conserved. Energy is also conserved as well. The law of conservation, if you're looking for why I skipped over that slide, I talked about the same information. So for the law of conservation, just like with matter, energy is conserved. So all the energy that is present at the beginning of a process is also present at the end of the process. All that we see in the terms of a reaction or some kind of physical or chemical change is the transformation of that energy from one form to another. So kinetic energy being turned into potential energy being turned into kinetic energy, or maybe the conversion of one form of kinetic energy to another form of kinetic energy, molecular motion turning into electrical energy. Regardless, what we're going to see is that from a conservational standpoint, matter, mass, energy, none of those things can be created or destroyed. All we're talking about, all we're seeing is conversions at best. In the conservation of mass, we can talk about the conversion of one substance to another substance in a chemical change. From an energy standpoint, we can talk about the conversion of potential energy inside of bonds being converted to thermal energy as that energy is being released as new substances are being made in the chemical change. So that's where we're going to end for today. So in your pair deck, you're looking for slide 6. So what do we have to look forward to on Wednesday? So on Wednesday, we are going to look at what are these different forms of energy and how do we start to quantify them? So we've kind of taken a step in terms of defining each of these forms of energy. On Wednesday, we're going to start to look at, well, how do we measure energy? How do we convert from one energy form to another? And then how do we do things like measure temperature, convert temperature from one scale to another? And that's going to basically be where we wrap up this particular chapter. So in terms of new stuff, Wednesday is going to be new, but like these conversion factors, do you understand dimensional analysis from chapter 2, converting one unit to another? That's all that we're doing here. We're just putting a different kind of unit to it. So instead of distance or volume, now we're talking energy. And then we're also going to talk about temperature, Fahrenheit scale, Celsius scale, Kelvin scale, and how to convert from one to the other using equations. And that's largely the extent of what we're going to do. So make sure that you answer that checkpoint question if you have done so. That's all that we have for today. Have a great afternoon.